Okay. Hi, everybody. Thank you for joining us. Our work is titled A Quantum Neural Network for Fraud Detection Using a Data-Driven Priority Entanglement Scheme. My name is Yusuf Halik. I'm one of the authors. I'm the first author, and my email is here attached. And the second author is Donglin Wang. He was actually my PhD advisor. We are both from Middle Tennessee State University in the Computational and Data Science program. So I'll be going over the usual items here: introduction, background, methodology, results, discussion. And in the background, I have some essential quantum computing, quantum machine learning concepts, just in case there's someone in the audience that isn't quite familiar with these things. I'll probably breeze through that. We only have about 20 minutes. So we'll start with the introduction. So this work is motivated by financial fraud. Okay, so financial fraud costs banks and financial institutions millions of dollars a year. They are often highly imbalanced data sets, meaning there are tons and tons of normal transactions, and a very small percentage of that data set are the fraudulent transactions. So the task of classifying those fraudulent transactions, finding those fraud transactions, meaning like somebody maybe stole your credit card and started using it. How can the bank text you so fast saying, hey, was that really you? That's a classification problem. So we hope that in our work, we try to find an advantage in using quantum machine learning, mostly based on the richer expression that it can provide, meaning finding deeper and more meaningful patterns within that data set. And the data set we use is a Kaggle data set. Is kind of a little bit famous. I think in 2014 it was created and is widely used, kind of a benchmark for fraud detection. It's called credit card fraud transactions. These are real data, real transactions from a bank in Europe. I'll be going over the data set in the methodology section. And XGBoost, logistic regression, and support vector machines, those are the classical baselines and classical models that are traditionally used along with neural networks. Now, what I really wanted to do in this work was provide a fair comparison, the most apples to apples comparison I could between classical and our hybrid quantum neural network. A lot of times in papers, you'll see papers claiming, oh, they got this metric higher compared to the classical, or something was better and we achieved quantum advantage. However, oftentimes the classical baseline is not optimized. It's just kind of off the shelf. So we wanted to make it the most fair fight, and with the hopes of really pinpointing what the quantum component actually added to the experiment. What did it, we wanted to provide as much evidence as we could to show that switching out a classical component with a quantum component really improved the results. And so the ultimate goal is to classify the fraudulent transactions in this data set. We're mainly going to focus on recall, precision, and PR AUC, mostly recall. Recall is essentially, how many fraud transactions did we catch and how many did we miss? And so we focus on recall a lot in this work. Here are some of the backgrounds you'll need to know. I'll just briefly go over these. You have to be familiar at least with the concepts of qubits and versus classical bits, superposition, entanglement, quantum gates. I'll kind of tie things together and put it in a data science context. There's something called a block sphere and the Hilbert space that will help us kind of visualize what's happening here. And then you put it all together to create something called a variational quantum circuit, or a parameterized quantum circuit you might hear. And all of this is essentially an evolution in the way information is processed. Okay, so of course you are probably familiar with the classical bit is represented as 0, 0, and 1, whereas the quantum bit is 0, 1, or some combination of both. This is a quantum mechanical phenomenon called superposition. And again, this is just all an evolution in the way information is processed. And here you have some equations, but we don't really need to focus on the physics or the quantum mechanics part. Just need to get a basic understanding of what's happening under the hood. You have superposition and you have entanglement. These are the two quantum phenomenon that really enable us to evolve our computation. And entanglement especially, it's when two qubits are correlated in such a way that the states of each other affects each other. So this kind of enables us to achieve a sort of parallel processing of information, a coordination and information sharing within the network. And we're really leveraging a new type of entanglement scheme in this work. And then you have the quantum gates. So how would you naturally manipulate classical bits? You would do that with logical gates, right? Classical logic gates. And it's the same concept in quantum computing. You would manipulate qubits using quantum gates. The most common are the Hadamard and the controlled NOT gate. We don't use the Hadamard gate in this work, but we use a lot of the controlled NOT gate, the C NOT. That simulates entanglement, and these are just unitary transformations. And so to tie it all together, there is classical data, which is what we're used to, and there's quantum data. So when we are integrating a quantum component into a classical neural network or any kind of classical model, we have to encode data into quantum data. You take the classical data, you encode it into quantum data, then you process it, and then you decode that data back into a classical vector, and then continue to process the data. And one of the important things to note for this model is that each qubit is mapped to a feature in the data set. We're about to get to the data here, but there are 30 features in this data set. So we don't need 30 qubits, which there's another method we incorporate called re-uploading. I'll get to that soon as well. And then we use the entanglement to kind of mix the information. And then at the end, the expectations of each qubit are measured. And a block sphere is a kind of a geometric representation of a quantum state. It helps us kind of visualize it. This is the quantum state of one qubit here. And Euler rotations, or a rotation gate, will help us achieve any point on the surface of that block sphere. And any point on that surface means that the qubit is in a superposition state. And if you'll notice that the rotation matrices has a theta value, that is what is actually parameterized. And these RZ, RY, RZ, this is arbitrary. It could be RX, RZ, RX, or any combination of X, Y, and Z. Those are parameterized rotation gates, which helps us achieve rotation. And the key is that they are parameterized, meaning that theta value can be learned and updated. Just like the weights in a neural network can be learned, this is what's being learned in the quantum neural network. And if you just integrate a VQC into a machine learning model, into any kind of classical model, then it becomes it becomes a hybrid quantum classical machine learning model. This is just a basic VQC. I'll share a figure of the one that we used in our hybrid model, but I just wanted to illustrate that you have your four qubits here, and then your rotation gates putting the qubits in a state of superposition. And then this is entangled. This is a C0. These are the C0 gates entangling said qubits. This being 1 to 2, 2 to 3, and 3 to 4. So our work essentially is finding a new way, or a kind of unique kind of bespoke way of entangling these qubits based on the correlations of the data we find before we process anything at all. And I'll get to that here in a second. So the data set, again, this was from a Kaggle data set. These are 2 days worth of real credit card transactions from a real European bank. It's highly imbalanced. So in this case, there are 280,000 normal transactions versus 492 fraudulent transactions. So it's basically a needle in a haystack situation. There are 30 anonymized PCA-like features. Only thing that's not anonymized is the amount, and I think a time, which we convert time into like a bucket. And because of one of the major limitations of quantum machine learning, which is the data loading problem, we have a hard time processing large amounts of data, and 300,000 records isn't even that much. We decided to downsample the normal transactions down to 10,000 while keeping all the fraud. We did not want to upsample the fraud transactions. There's many techniques like SMOTE and other variations of SMOTE that created noise, that caused overfitting, that had a bunch of issues. So we kept all the fraud as is, 492, but we downsampled down to 10,000 normal transactions with a 50, 25, 25 training, validation, and testing set split. Very important. A lot of papers you'll find has no validation. If you don't have validation, you have to do something called cross-validation, and they won't have those distinctions, making the experiment a little bit kind of polluted, you could say. So it's very important to outline this information. Each model had 10 epochs with 100 runs. Another distinction in our work versus most others is that they will maybe just do 1 or even 10. 10 is okay, 10 runs, but you really want to establish a confidence interval, get some averages of your results, because if you just run it one time and you get a good result, it could easily be a fluke. It's hard to pinpoint exactly what was the cause of the better or worse results. So we want to make sure that we are providing the best quality. Atom, ReLU, TANH, all standard stuff, a 0.001 learning rate. And then the architecture of the quantum neural network, it had 2 linear layers with the activation function, and then an interchangeable middle layer. I'm about to show the architecture here on the next slide, but then a shared classification layer at the end. So here's a shared classical trunk. Again, this is hybrid, right? This is a hybrid quantum classical neural network. So it has a shared classical trunk. And then the quantum model goes in this direction with a quantum circuit. That's where we have our variational quantum circuit or parameterized quantum circuit. I'll show that, what that looks like in the next slide. And then the classical model continues on with just another linear layer with a TANH activation function. And then they both continue on and classify here at the end. Was it fraud or was it normal? So it's a very simple architecture. We just have this interchangeable middle layer here. Now I want to bring up the priority pair entanglement scheme. What does that mean exactly? So instead of a default entanglement scheme, there are, I think, 3 defaults. There's ring, there's full, there's something else where in Penny Lane or whatever package you use, you can just use some default entanglement. So in this case, this was, I think, ring. Ring would be kind of tying it back to so that all the qubits are entangled just kind of sequentially, 1 to 2, 2 to 3, 3 to 4, 4 all the way back to 1. That's ring. Full entanglement would be every combination of these 4 qubits would be entangled. We use the ring, but before that, we use the priority pair entanglement. I got ahead of myself here. So how did we come up with a priority pair? First, before processing anything at all, we found the most highly correlated by Pearson correlation features in the data. And then we entangled those features first. So if, let's say, feature 2 and feature 27 were highly correlated, we mapped those qubits to those features, and we entangled those qubits first. And then we used the standard ranks. So there was a kind of grouping of features together, aka qubits, and we entangled those features and qubits first, right? The intention was to sort of guide the optimization. The optimization landscape, the loss landscape in this problem was that you suffer from barren plateaus, all sorts of things, and local minima, maxima, whatever, and so guiding the optimization helped us the idea was get to the best solution faster, more efficiently. So you have something called angle embedding first. I won't touch on that, but then we implemented our priority pair entanglement here, which is going to be, I couldn't really portray that, but that would be some combination of these qubits. And notice here, these are 10, but I had 30 qubits, right? So I had to use something called re-uploading, which is where when you don't have enough qubits to encompass in our case, 30 features, we chunked them. 10 qubits, 10 times 3 equals 30. So there were 3 chunks. For 15 qubits, which we also did an experiment with 15 qubits, we used 2 chunks. And then we reordered the features so that the chunks contained the priority pairs within them. So the chunks can have an inter-chunk like loss of connectivity, but we chunked the most correlated features together so that we could have the best results after that. So you do the priority pair entanglement, and then this is just your standard BQC implementation after that. So now we get to some of the results. Before I get to the quantum results, here are some of the classical results we got. we had to compare it against the classical neural network, right? And that had the best recall of everything. And these are, again, 100 runs. So 0.88 recall out of 125 fraud transactions in the test set. That was like, say, 17 recall, 17 fraud transactions that we missed, that we didn't get. And then after that, they got a little worse with the logistic regression, XGBoost, support vector machine. So 17 fraud we missed, right? Now, when we get to our 10 qubit model, again, 100 runs, 10 qubits, and then how also the number of priority pairs we implemented was also a significant factor. When I maximized how many priority pairs we used, I got the best recall of 0.9235. This translates to 8 or 9 fraud transactions that we missed, 8 or 9 that we missed. So a significant improvement. But you'll notice that precision started to suffer. Here, our precision stayed pretty high. It wasn't great for the neural network, but it was in the 0.9 range for the other classical models. Precision was always around 0.5 to 0.6 or so for the quantum models. But then the most interesting thing was with the 15 qubit model, where we achieved the best recall of 0.97 with just 10 pairs. So the 10 most correlated features, we entangled those. 0.97 means 3 or 4 fraud. Okay, 3 or 4 fraud. That's a huge difference versus the 17 that the classical neural network obtained. So we only have a few minutes left after go through the rest here. Here is the model summary. So roughly 2,300 for both. Again, we wanted the most apples to apples comparison. And again, one thing to note, that precision also went down a little bit more. Precision was how many false alarms did we have? How many normal transactions did we get? And how many did we miss? So that got a bit worse, but it wasn't that bad. And we want to focus on recall because you would rather have a false alarm instead. If you're a bank, you want to have a false alarm instead of missing the fraudulent transaction. Okay. So our main finding was that when we replaced one dense layer with the quantum layer, it had a major impact. And then when we had the data-driven entanglement approach, the priority pair entanglement scheme, that was very impactful. But then the most interesting thing was when we quote unquote boosted the quantum power by making 15 qubits and 2 chunks versus 10 qubits and 3 chunks, that significantly lowered the recall. What I mean is it increased the recall, meaning that it lowered the number of fraud transactions that fell through the cracks from 17 or so with classical down to 8 or 7 or 8 or 9 with the 10 qubit model, down to 3 or 4 with the 15 qubit model. And then it made it even better with the priority pair entanglement scheme. Over-parameterization had an impact. If you'll notice, we also implemented a certain number of quantum layers. I skipped 3 quantum layers here. That for some reason always reached a barren plateau. It classified all the transactions as fraudulent, thereby getting a perfect recall and a horrible precision. So we don't want that. So over-parameterization was something to consider as well. But then the main, one of the biggest bottlenecks was the CPU time. These 10 qubit models, at worst, they took maybe an hour to run for each epoch. And the 10 qubit models, the worst one was almost 15 hours to run one model. And so that's why also I forgot to note that these were run for 20 times rather than 100, just for the sake of time. But we achieved, I think, quite meaningful results here. And that's basically the work. We wanted to provide the clearest evidence for the effect of a quantum component, the hybrid quantum classical model, and we wanted to provide the fairest comparison against the classical methods as well. There's still a lot of work to be done. There's much more experimentation that could be done here. There are other correlation coefficients that could be used as well. And this was actually the first chapter of my PhD dissertation and something that I developed during an internship as well at a financial institution. So thank you all so much. Here are some references, and I hope you enjoyed it. If you have any questions, you can reach out to me by email. Thank you.